Hello everyone and welcome to this video on autorotations. So autorotations is a big topic in helicopter flying. In fact, there's an entire book dedicated to this topic. It's called The Little Book of Autorotations by Sean Cole. That's actually mostly an excerpt from a much larger book of his called Cyclic and Collective. Both of them are good books, but I wanted to try to have a brief coverage of autorotation. So, first of all, what's an autorotation and why would you ever want to do one? Well, an autorotation is something that you're forced to do if your engine fails. If your engine fails and you don't have a motor to drive the main rotors, then you have to do it some other way. Well, how does that work? So if you look at the figure, you'll see that in normal flight, you're going forward and you're sucking air down into the rotor. You have that induced flow that we've talked about in previous videos. In the case of an autorotation, what you're doing is you're descending, as shown in the right hand of this picture, and that is forcing air up into that rotor, and that air being forced up into the rotor causes it to turn. Now, how is this physically possible? It's physically possible because of something in your aircraft called a freewheeling unit. And what it does is if the rotor RPM becomes greater than the engine RPM, it will disconnect the engine from the rotor, and this allows the rotor to turn by itself. Now, some manufacturers like Robinson, they call this a Sprague clutch, but it's the same thing. It's a freewheeling unit. So back to autorotations. You have this rotor that's spinning, and that allows you to control your flight. So believe it or not, statistically, you're better off in a helicopter with an engine failure than in an airplane, which might seem kind of counterintuitive, but the biggest reasons for that is a helicopter, you can stop it before you land. Now, you might not be able to get it to completely stop. You might still have some forward speed. You might still have a little bit of a vertical descent, depending on the situation. But it's better than the situation with an airplane where you're going, let's say, at least 60 knots when you hit, and you need a much larger space to do an emergency landing in an airplane. So how does this rotation work? Well, here's a picture of what things look like if you're doing a zero airspeed auto rotation. Now, this is not a recommended thing. This is just kind of a starting point, if you will, of discussing the aerodynamics of this. So all of this, of course, comes out of the Helicopter Flying Handbook. This is chapter 2, which is all about aerodynamics. And you have these 3 different regions. So the inner region is the stalled region. What does that mean? The speed of the air going over this region is pretty small, and it's going to be stalled. So it's not producing any lift out there. Then we have this inner region, which is called the driving region. It is producing lift, and that lift is tilted forward. So that forward tilt of the lift, the total aerodynamic force, if you will, being produced by that airfoil as it spins, is tilted forward. So that causes it to drive the rotor around. And then we have the outer portion where we have the driven region. That aerodynamic force is tilted backward somewhat, so that is going to try to slow down the rotor. But it's still producing lift. It's just that that lift is tilted backward. So if we look at another picture here, we can see what's going on. So out here at the tip in the driven region, we see how that total aerodynamic force is tilted aft, and that's causing some drag. And that's why we see that it says there's drag here. Then we have these equilibrium points where it's not producing drag or it's not producing a driving force either. So here in the middle region, this driving region, we can see that total aerodynamic force is tilted slightly forward. And then in the stall region, we're not getting any lift. We're pretty much just getting drag. So that's what things look like if you had zero airspeed. We don't normally want to do an auto rotation with zero airspeed because that's really, really rough, especially on the landing part, which we'll get to here in a little bit. So now if you say, well, what happens if I'm actually going forward when I do this auto rotation? If I'm actually going forward when I do this auto rotation, now what's going to happen is that these regions are going to get pushed toward the retreating blade. So in the case of an American helicopter like the Schweizer, it's going to get pushed to the left. So that's how the aerodynamics change if you're in forward flight during an auto rotation. Some more boring theory before we actually get to flying here a little bit. So as we said before, you have the auto rotation, you've got the air flowing upward through the blades. Now, how do you do this auto rotation? Well, you're going to start at position 1 where you had an engine failure and it's time to do an auto. Now, first question, how do you know you've had an engine failure? Well, the helicopter is going to start to yaw. And which way is it going to yaw? It's going to yaw to the left. Again, if it's an American helicopter. It's going to yaw to the left, and that yawing to the left is telling you, hey, you're losing power. So, your need for left pedal has decreased, and therefore you're going that way. So as soon as you detect that yawing to the left, you want to begin your auto rotation. And how do we do that? Often people will say down, right, aft. So you drop the collective. Why do you want to drop the collective? Rotor RPMs are life, right? If your rotors spin down too much, they will never spin back up, especially if you're flying something like a Robinson that has a low inertia rotor system. Helicopters are rigged so that if you have the collective full down, you can do an auto rotation. That is part of the way that they're set, right? So if you drop the collective fully and you aren't able to maintain RPMs, unless you're in something like a high density altitude situation, most likely what that means is that your helicopter is misrigged. Okay, so you're going to immediately drop that collective. Now, of course, when we practice, we drop the collective, then we roll off the power. Now, when it comes to rolling off the power, by the way, you don't have to go all the way to idle. You just have to split the needles. So in previous videos, I showed you a picture and I said, hey, this is how you should be holding the collective, right? Use your first 2 fingers and your thumb to work the throttle. Use your pinky and your ring finger in order to lift and lower the collective. One thing you can do is when you're practicing these auto rotations, if you put your fingers up, fingers to the sky, if you will, and then drop the collective, roll off the power. So it's down, right, aft. Right? So down, then right pedal. Why right pedal? Because it's going to start yawing to the left. And then aft. Why aft? You want to maintain a certain speed. What speed is that? It's going to vary from one helicopter to another. We'll talk a little bit more about that later. You want to pull aft on the cyclic, and that is going to do a couple things. First of all, it's going to keep the nose from just dropping when you do this, right? You think about it. You just lower the collective. So the helicopter wants to descend, and it tends to drop the nose. So you want to pull back. And how much do you want to pull back? Well, you're not trying to flare here. You're just trying to keep the nose in a reasonable place. So let's say you were doing 60 knots when you entered this auto rotation, which would be a somewhat common entry speed. So you're doing 60 knots, you go down, roll off the power, right, aft, you're looking out in front of you, and you're trying to maintain that same pitch attitude. Okay, so now you've gone from position 1 to position 2. Eventually, you have to land, unless your power got miraculously restored somehow, and you'll get to position 3. So position 3 is where we start to transition from what's probably a pretty rapid descent. You're probably looking at something like at least 1,500 feet per minute. Possibly more depending on the conditions. So how do we do that? Well, we pull back on the cyclic. And what does that do? It starts to arrest our descent, number one. And number two, it's going to cause coning of the rotors. So as the rotors cone, they speed up. And we want that, right? As long as we're within the limits, we want that because we want to get every bit of energy out of that rotor for the last 2 stages. So we're going to come in about roughly, let's say 50 feet in the air. We're going to pull back, and then, we're going to watch our RPMs. If our RPMs start to get above the green arc, then we might have to check a little collective. Just check it up for a second in order to keep things in the green. And then as we've dissipated our speed, we're going to level the aircraft. That's position 4. So we're going to push forward on the stick, and then we're going to descend. And as we touch down, we are just going to pull up on the collective in order to hopefully touch down somewhat softly. So of course, what I've just described is what we call a full down auto rotation, which is often not what you do for practice. And you might say, well, why not? The biggest reason is that they were destroying more helicopters than they were saving by having everyone do full down auto rotations. It's sort of like the airplane world. In the airplane world, they used to make people do spins. They had to demonstrate spin recovery for their check rides. And they found out they were losing more pilots and planes from the practice than they were from people actually getting into spins and not being able to recover. So they changed things. So now only flight instructors have to demonstrate the ability to recover from a spin. The same thing is true in the helicopter world. Only flight instructors have to demonstrate the ability to do a full down auto rotation. Okay, so let me back up just a second. And some more theory. Sorry. That's auto rotations. It's kind of a complicated thing. So we said you started your auto rotation. You said down, right, aft, down collective, right pedal, aft on the cyclic in order to maintain that pitch attitude. Let's say it's for 60 knots. As you're coming in, what are you going to do if your speed starts to decay too much? There's a recommended speed. Different manufacturers are different in their manuals. So Schweizer, their manual is not very specific at all. And they'll just say, hey, you should go, 52 knots is kind of ideal. Most people will come in at 60 knots. So 50 to 60 knots in a Schweizer seems to work just fine. So if you're going too slow, well, then you push forward a little bit. If you're going too fast, you pull back a little bit. Now, there's a relationship, though, between that speed and the cyclic and your RPMs. Right? So if your RPMs start to drop, if you pull back on the cyclic, it will cone the rotor and cause the RPMs to go up. So you're going to load up that rotor and cause it to actually speed up a little bit. If you're within that range on your RPMs, let's say you're starting to exceed it, then you can use the collective. You can pull up the collective a little bit and keep you from exceeding the RPMs. So, you can't necessarily just use one or the other to make this work. Auto rotations are complicated. Some people will say there's no such thing as a by the numbers auto rotation. There is a little bit of feel. You can't say, oh, well, if I pull the collective up this much, then, it'll all work out. There's also things like, can I stretch my distance to my spot? Let's say I'm not quite going to make it. I can if I increase my speed and lower my RPMs, again, keeping within the allowable ranges, I can go slightly further. Now, the Schweizer manual is completely silent on this. Maybe they figure, hey, you don't have a lot of effect if you bother to do that, this particular helicopter, and maybe that's why they don't really even mention it. So that is very basics of a straight-in auto rotation. I'm going to go ahead and demonstrate a few of these right now. Let's go ahead and fly it. I'm going to try to talk through it as we fly it. And, again, things happen kind of quickly. So, that's why we're having this discussion first. All right, entering in 3, 2, 1, down, aft. Trying to maintain that 60 knots or so. RPMs are well within the range. Looking at my spot. Spot looks good. Speed looks good. RPMs look good. So spot, speed, RPM, spot, speed, RPMs. Right about here, we're going to start to flare, 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 flare. Pushing and pulling as we roll out the power. New cover. Picture. RPMs look good. Spot, speed, RPMs. Spot, speed, RPMs. Spot, speed, RPMs. Looking good, looking good, looking good. Flare, flare, flare. Push, pull, rolling out the power. Like that. Pushing, and we're going to pull. So that's a full down auto. Again, not something that you normally do unless you're a CFI applicant or you have an actual engine failure. Now, one thing I should say, earlier we were talking about why do you do auto rotations. There are other situations in which you might want to do an auto rotation. It's not just in the case of engine failures. For example, let's say that you lose your anti-torque system. You have some sort of failure there. Well, unless you want to start spinning like every helicopter in every movie or TV show right before it crashes, what are you going to do? Well, going to enter an auto rotation. Some people say, when in doubt, auto out. That is certainly something that you could do in real life. You get rid of that torque, and then you do an auto rotation to a landing somewhere. Now, depending on the aircraft, sometimes the manufacturer will say, if you maintain this forward speed, maybe a little bit of cyclic, then keep it sort of straight. And why would you do that? Well, you might want to do that if you weren't over anything that you wanted to land on at that exact moment. Is pretty much all I wanted to say about straight in autos. Hopefully you liked this introduction. Again, standard disclaimer, this is not to be substituted for actual flight instruction. See you guys later.